Classification algorithms are a type of supervised machine learning algorithms that try to assign classes to each of the labels. So in the slide that you can see there, it's trying to find what is the line that separates two groups of samples. And this line we call a decision boundary, and it can either be a straight line, in which case we say that the problem is a linear problem, or that it is linearly separable. And if it's a curve, we say that the problem is a nonlinear problem. So what types of classification problems do you think we see in healthcare or in mental health scenarios? Classification problems can be of three types, one of three types. It can be binary, meaning yes or no, so differentiating between just two classes. It can be a multi-class classification if we have a categorical variable with more than two categories and we need to associate each sample to only one of those categories. Or it could be a multi-label classification problem where one sample can be assigned to more than one category at the output, correctly assigned to more than one category at the output. So go back to the problems that you defined earlier, classification problems, and assign types between binary, categorical, binary, multi-class, and multi-label problems. Most classification problems in healthcare in general and in mental health as well are binary problems. So we try to differentiate between often healthy or not healthy. That's often the kind of problem that we encounter. It's not the only one, but it's often the kind of problem that we encounter. Let us focus then on binary classification problems, as these are the most commonly encountered in this setting. And we should now define what are the quality metrics that we can use to assess how well the machine learning algorithm is performing in these type of problems. So we begin with a confusion matrix, and in this case, I have defined, so this is a 2x2 table, and I have defined targets, so the true targets on the different rows and the predicted labels or the predicted values on the different columns. And we can see how this is just a tabulation of these two variables. So we just want to see ideally how all the positive samples are classified, are predicted as being positive, and all the negative samples are classified or predicted as being negative. Let me highlight here that these positive and negative names that I'm using, these are typical for machine learning. It does not refer, it's not related with the positivity of the outcome or the negativity of the outcome. In fact, in this context of predicting, for example, whether a patient is suffering from depression or not, it's going to be the other way around in terms of positivity and negativity. We will define the positive samples as those of patients that suffer from depression, and the negative samples as those that do not suffer from depression. Generally speaking, positive samples are the cases that we want to find. So why are we developing this algorithm? Because we want to identify those that are suffering from depression. So then those will be the positive samples. And then from this confusion matrix, we can extract a number of quality metrics. Here is a list. These are by no means all the quality metrics that we can extract from a confusion matrix. matrix, but they are the most commonly used. So we have the true positive rate, called sensitivity, or also called recall, and this is just the proportion of positive samples that are correctly identified as being positives. Then we have the true negative rate, also called specificity, which is the proportion of negative samples that are correctly classified as being negative. We have the positive predicted value or prediction, and this is the proportion of samples predicted as positive that were really positive. And we have the negative predicted value, which is the proportion of samples that were predicted as negative and that were truly negative samples. We have accuracy, which is just, okay, of all the samples, how many did we correctly classify, or the proportion that we correctly classify. But again, remember that one of the characteristics of this type of data is that it's going to be highly imbalanced. We're going to have way more samples that belong to this positive class that belongs to the negative class than samples that belong to the positive class. So using accuracy in this scenario is not a good idea, because in the extreme, let's imagine that we have 100 samples in total, 99 of them are negative, one of them is positive. If we have a machine learning algorithm that just predicts negative for all the samples that we pass through them, then because of the way the data is organized and because of the high imbalance, that means that it's going to correctly classify as negative 99 samples out of the 100. And the only one that is positive, we're going to incorrectly classify it as negative, but it's only 1 out of 100. So the accuracy is going to be 99%. As you can imagine, that model, that 99% doesn't correctly depict how well that model performs. An alternative to this is to use balanced accuracy, which in a sense is just the average between the true positive rate and the true negative rate, or the average between sensitivity and specificity. Another really, really good quality metric is the Matthews correlation coefficient, which is it's the square root of the product of true positive rate, true negative rate, positive predicted value, and negative predicted value. So why is then the Matthews correlation coefficient interesting? And the reason is that being a geometric mean of all these four metrics, whenever one of these metrics is low, then the MCC, the Matthews correlation coefficient, is going to be low. So the issue that we have, or the difficulty that we have, is that it's very hard. There is no one single metric that fully defines the composition of the confusion matrix. So just using the balanced accuracy doesn't tell us, for example, how well the model predicts true positive samples, or how well the model predicts negative samples. It gives us an average of those two. And actually it doesn't tell us about, well, of all the samples that we predict as positive, how many of them were positive. So it doesn't tell us anything about the positive predicted value or about the negative predicted value. The Matthews correlation coefficient combines all these metrics that we really want to maximize. We want to maximize sensitivity, we want to maximize specificity, we want to maximize PPV, and we want to maximize MPV. So that is why the Matthews correlation coefficient is it's a very useful metric to use when we are optimizing machine learning algorithms, or when we are evaluating machine learning algorithms. Now, even though we are talking about classification algorithms, a classification algorithm doesn't always output a class in itself. So it doesn't output a categorical variable. Often it outputs a value. Again, if we are talking about a binary classification algorithm, you can imagine that value being between 0 and 1. And then the higher that value is, the closer that value is, you can think the most confident the machine learning algorithm has that that value is of class 1, it's a positive sample. And if the value is closer to 0, that means that the more confident the machine algorithm has that the value is of class negative. So that value between 0 and 1 in this case, it doesn't have to be between 0 and 1. It's typically between 0 and 1 because it's easy to interpret, but it could be between -1 and 1 or any other range that you want. That value is what we call a score, and it's a continuous value. So then what we need to do is to actually apply a threshold and say, okay, again, going back to the example between 0 and 1, we can say if the score is higher than 0.5, then we are going to say that the predicted class is positive, that we are predicting that this sample belongs to the positive class. And if the value of that score is below 0.5, then we are going to say that the predicted class for that sample is 0, is negative. We can also extract information about how well the model performs, how well the model behaves by analyzing the scores rather than the classes themselves, so before binarizing the score. And this is actually where the receiver operating characteristics curve, or the ROC curve, comes from. So on the slide there, you can see on the left-hand side, that is the conditional distribution of classes with respect to the predicted score. So we can see that lower values of the score are characteristic of controls, of negative samples, and higher values of the score are characteristic of cases, of positive samples. On the right-hand side, what we have is the axis of the ROC curve. So on the x-axis, we have 1 minus specificity, and on the y-axis, we have sensitivity. We also have a diagonal dotted line that goes from the bottom left corner to the top right corner of that panel, and that represents chance. So values within that line are equivalent to just flipping a coin on the air. So we're not really doing anything useful if we fall somewhere within that line. So how do we go about building the ROC curve? Well, we set a threshold. That threshold, we have represented that threshold as that vertical dashed line on the left-hand side. And then based on that threshold, we said, okay, everything that falls to the left of that line is going to be classified as a control, as a negative class, as a negative sample. And everything that falls to the right of that line is going to be classified as a case, as a positive sample. And based on that, we're going to get a value of sensitivity and a value of specificity that we can then represent on the right-hand side on the ROC curve, as we have done. And we can try another value of the threshold, and that will give us a different point of the ROC curve. And we can try another value, and that will give us a different point in the ROC curve. And if we do this for all the possible values of the threshold that we can try on the predicted score, we end up building the full ROC curve. Now, we want the ROC curve to be as close to the top left corner as possible, because that is the corner that has perfect sensitivity, so sensitivity equals 1, and perfect specificity, specificity equals 1. Note that the x-axis is 1 minus specificity, so that's why it's 0 on the graph there. So yes, we want a ROC curve that is as close as possible to that corner. There is also another diagonal line, which is the opposite to the chance diagonal line, which is the one that goes from the top left corner to the bottom right corner, and this diagonal line represents the point of equal error rate. So what does that mean? Well, it means that wherever the rock curve crosses that line, that's the point where sensitivity and specificity is equal. And that is the point where the balance accuracy is maximized. So again, ideally, we want our machine learning algorithm, we want to set a threshold that is as close as possible to that equal error rate point. Again, assuming that we are equally interested in maximizing sensitivity as we are in maximizing specificity, which is not necessarily always the case. It depends on the problem and the application. And then we have the C statistic, or the area under the rock curve, which is the shaded area now on the graph. And this is also often depicted to measure how well a model performs. If you think about that diagonal chance line, if we had a rock curve that is identical to the diagonal chance line, that will give us a C statistic of 0.5. So a C statistic of 0.5 means the model is a pretty bad one. So that would be the equivalent of a model that just flips a coin. And then anything that is high between 0.5 and 1, which will be the maximum, will be an improvement compared to 0.5 to the chance model. Now, what are the issues with the rock curve? Well, think back to how we computed the rock curve. We computed this curve by trying all the possible thresholds on our scores, on our produced scores, on our computed scores. However, the threshold is another parameter of our machine learning model. And as we said many times, all the parameters of the machine learning model need to be fixed and frozen before we do the validation. So before we measure how well the model performs on our validation set. So that means that we don't really have that, in reality, we don't have the liberty to just move the threshold later on to, okay, move around the rock curve to see how well the model performs for different thresholds. We don't have that flexibility. We need to set the threshold beforehand, and then that threshold will give us an operational point within the rock curve. Now, based on that, in my view, the rock curve gives us an idea of how the model can behave, or how the model behaves as we move the threshold up and down. But again, in a real scenario, once you set the threshold, you don't touch it, okay? And there may be occasions where the threshold, the intuitive threshold potentially of 0.5 that we set on the training data, then when we get to the validation data, it's actually far off the ideal equal error rate point, okay? So that could happen, and we don't have the liberty of, oh, I'm going to move the threshold now so that it fits my validation set. We can't do that, remember. In general, I have given you here a paper about the problems of using the rock curve that I think will be interesting for all of you to go through. Particularly because, again, when you go through the literature, the rock curve is a metric that is highly used. The C statistic, the area under the rock curve, is a metric that is very highly used to assess how well a model performs. And as I said earlier, I don't think that is necessarily a good, the best strategy. So again, personally, if we were to rank quality metrics, I will first use the Matthews correlation coefficient. There is a paper there discussing how these coefficient outperform others, or how this metric can outperform others. I will then use the balance accuracy, and then I will, my third option will be to represent all the four statistics that we want to optimize, that we want to maximize: the sensitivity, specificity, PPV, and NPV. Again, personally, the area under the rock curve or the C statistic is not something that I use, but again, I have given you some papers justifying this, but then again, it's up to you.